So I'll continue with this morning's high redshift issues. And it is about the cosmic web, but mostly this kind of web coming in. So the outline of my talk is how JWST reveals a puzzle, which is very interesting. I will try to suggest a solution, which I called feedback-free starbursts, or FFB, and I'll try to convince you that at cosmic dawn, around redshift 10, massive galaxies must form this way. So this is what cosmic web and JWST web is looking at, and I in particular take as an example today the SEERS survey. So far, 24 galaxies, you see them here. It's not very impressive pictures when you look at them at redshift 9 or 10, but these are the galaxies that in this first this survey, and this is the redshift distribution, photometric redshift, but they seem to be quite accurate as you start doing spectroscopy, between redshift 8.5 and 11.5. So here's the kind of puzzle that comes up. You look at the halo mass function. Avishai is here, but he is one of the fathers of the halo mass function. The number of halos above halo mass, given halo mass for lambda CDM, as a function of halo mass, and for different redshifts. So focus on this redshift 9 or 10 galaxies. The key is that we have an estimate of the volume, effective volume, where this sample of galaxies is coming from, as a complete set for a given luminosity. So you can ask for the first galaxy, if this is the volume, then you expect it around here, and you expect it to be of a halo mass of 10 to the 11 solar mass. If you look at the fifth galaxy, it is just a little bit below that, 10 to the 10.8 or so. So the halo mass estimates are quite robust. And that's for the fun. Let's talk about the 5 brightest ones. Now, much less secure is the stellar mass, which you do by SED fitting, but you have to assume an IMF and star formation history. You get something of this sort, but their mass is huge. But still, this indicates a problem, because if you define an efficiency of star formation, taking all the gas that was accreted, ask what fraction of it makes stars in the galaxy. This is the epsilon I'm talking about. Because the baryonic fraction is about 0.16, you find that epsilon must be around unity for this galaxy, if this is correct. And that's a puzzle, because as we all know, at lower redshift, even redshift 4 or maybe even higher, we have an efficiency of about 10%, and lower if you're talking about lower masses. So something is very different about these galaxies at high redshift. Now, there are certain possible solutions. One of them that the observation are totally off, and this will come in with upcoming more observations that are coming in very quickly. It's possible that we want to change lambda CDM and get a number density of halos that is higher. One possibility is the EDE model, where you was introduced to solve the Hubble tension, some inflation, 10% of the energy, added just before recombination, some fine tuning, and you may end up with it. It also helps you to get some higher sigma 8, so a little more abundance of galaxies, of halos. Now, it's fine, except that if you adopt the Occam-Razor, you rather first try a solution within the standard model. That's what I'm trying here. A third possibility is that M over L is different. somehow there's much more luminosity per stellar mass in those galaxies. And this you get by a different initial mass function or by UV from black holes. It's a possibility. I'm not sure it's going to solve the problem. And it has to have very low massivity, which apparently is not the case, to get really population-free stars. So today I'm going to tell you about a real high efficiency. Epsilon is really one. That's what I'm trying to talk about today, feedback-free starburst. So I'm going to tell you about what I mean by feedback-free. I'm going to tell you about how you get starbursts by cooling and how what you form is self-shielded. Just to illustrate the problem at low redshift, it's another wonderful picture of JWST. I think it's M74. Look at these bubbles. Supernova bubbles are really there. It's not a legend. They are going to suppress star formation in most normal redshifts. Somehow we have to overcome this to get epsilon of 1. And I'm trying to convince you that it's pretty robust, that at redshift around 10, it can be 8, it can be 12, 15, and halos of around just below 10 to the 11 solar mass, you must have epsilon of 1 by very simple arguments, feedback-free starburst. And this has to do with time scales of 1 million years, that's the free fall time at this epoch, which correspond to a number density of a few thousand per cc. It will come back again from many different ways. So what is this feedback-free thing? Look at the luminosity, mechanical luminosity from a burst of star formation, done by Starburst 99. As a function of time, you see this interesting behavior for focus on the low metallicity ones, the green and the blue. Now, this peak is for supernovae. There's always a gap of about 3 million years, independent of metallicity, simply the lifetime of the O and B stars, which are responsible for this big supernovae. But also the winds that supposedly were starting at the burst itself. If the metallicity is low enough, they're going to give you a delay before the winds become important. And that's this part of the curve. The reason is that you have to move the metals out by convection into the outer parts of the stars before they can generate the opacity for the winds to be affected. So you have a 2 million years around gap for the winds themselves. And together, this would be the binding energy of a cluster that I'm going to discuss a little later. So if the metallicity is below 0.2, maybe 0.1 and below, you really have the winds suppressed as well, and together the winds and the supernovae giving you this delay. So there's a robust delay for the supernovae, there's a wind delay once the metallicity is low enough. It doesn't have to be very low, just a little bit low in solar metallicity. So at low metallicities, there's a feedback delay of more than 1 million years after a starburst. I'm going to be very conservative and assume it's only 1 million years, but you see it's a little more. And this is what can give you a feedback-free starburst. If the free fall time is shorter than 1 million years, you can make all the stars in a burst before feedback even starts being relevant. That's the key idea. Now, in this picture of density and time, this is the feedback time, 1 million years, and this is the free fall time. And as you can see, they cross at this magic density. A few times, a few thousand. Now, a second condition for this burst to be feedback-free, is that you need to cool on a time scale that's shorter than the free fall time to start fragmenting and make stars. Now remember, we are in this regime where it's problematic. Below 24 degrees, the cooling time is very long. It's a molecular metal cooling, also depending on the metallicity. It's basically line cooling like this. This is the cooling time. I take this example of carbon-2. And you ask again, when is the free fall time and the cooling time comparable? And you find that it's the same magic density, pretty much. 3 times 3,000. Given the metallicity, the temperature, and some clumpiness factor. So it's the same. If you look at the cooling time, below 24 degrees, you end up with the same crossing, very similar to what we got from the feedback-free requirement. They all boil down to this magic density of a few times 10 to the 3 per cc. Now, the third thing you have to make sure is, since the times for infall in the halo are on the order of 100 million years at that times, not 1 million year, there's a continuous supply of gas that comes in via streams from the cosmic web. And you have to make sure that this population of first generation of stars that now start effective feedback are not going to ruin the new star formation regions by winds and radiation that can suppress the star formation. So we need to be shielded. In each of these clusters where the stars form, you have to make sure you are shielded. So what you can look at is the crunch time for clumps going through wind. It's basically the Kelvin-Helmholtz time scale or some other hydrodynamical instabilities. It has to do with the size of the cloud you're talking about, and the density in the cloud, and the wind that developed jointly by many supernovae and star formation in earlier generations, density and velocity in the wind. And you end up with a few million years here, and you have to compare it again to the free fall time and ask yourself, what is the mass of such a cluster that will make sure it can be feedback free? Namely, it's going to be shielded against this wind. And that's the condition. And you find that it's about 10 to the 4 solar masses. So clusters above 10 to the 4 solar clusters are going to be shielded against previous generation feedback. The same is true about the radiation. You can do a radiation. Remember, as we heard this morning, there's no UV from other bubbles yet. So it's only radiation from this population here. It's much less problematic. There's a very small penetration into a cloud like this of 0.1 parsec when the cloud is several parsecs inside. So that's negligible. You can also find that these clouds are coming in generations of about 1 billion solar masses. So if you have 10 to the 10 solar mass stellar galaxy, you're going to have 10 generations of this formation, the formation we were talking about. So the shielding in the same picture is for a 10 to the 6 solar mass cloud, which is the typical cloud. I'm going to talk about globular cluster size cluster. You are pretty much here protected from all the effects of the previous generations. So, is this really happening in our universe at redshift 10 and in massive galaxies? Let's see. A few numbers just for the feeling. We are talking about a universe that's less than 500 million years old. The halo size for the mass I just talked about is just above 10 kpc. The halo of the inflowing streams, the velocity is on the order of 150 kilometers per second. And the time it takes to cross the halo is about 80 million years at this redshift. And the accretion rate can be estimated analytically is on the order of 65 solar mass per year, which for epsilon of 1 is going to be roughly the star formation rate you expect. Prediction. Now, through the halo, the cooling is much more efficient. We are in this regime, as you all know, and the cooling time is much shorter than the real time or the free fall time, so it's all going down at 10 to the 4 degrees. In this diagram from Dekel and Birnbaum, we looked only out to redshift 5, but now it can be extended, the same calculation, to redshift 10, and you find that the galaxies we talk about can cool very efficiently as they flow in. It's in a cold flow regime. They flow in the streams of 10 to the 4 degrees. And you can ask what is the radius of the streams. So I asked again, what is the radius of the stream? And that's what he told me, something below 1 kpc from their simulations. The other ways to estimate this more analytically from cylindrical collapse, and you get roughly the same kind of. It's important for the calculations that come after that. So this is a redshift 6 galaxy, but maybe it looks like the one we are talking about. The streams fitting a galaxy, in this case a disk. I'm not sure at redshift 10 it's going to be a disk, but maybe. Look, that it's already clumpy disk right there. That's crucial for this cluster formation. So what is the epoch and mass where we expect feedback-free burst? That's the key now. So this is a bad picture. I'm checking two regimes, one in which the streams are pretty radial, and then you form a shock here in a shell. The other where the streams have impact parameter and you form a disk. So case number one is radial streams. You can convince yourself, and there's a paper by Dubois et al. With Christophe and Julien and others, where as a function of redshift, you find that you ask yourself, what is the height? How many sigma peaks we're talking about? It turns out we're talking about 5 sigma peaks. And the idea is that 5 sigma peaks do have pretty radial streams. So you can think about radial streams. That's from the paper I just referred to. Also, you see that they're pretty radial at redshift 6. I don't have anything at redshift 10. On the other hand, there are other cases where at low redshift you have a lot of impact parameter, that's the real radius. But still, in the same simulation by the same people, Dubois et al., you do form a disk with some low angular momentum spin. So you can think about those two cases. If you think about the radial inflow, you can compute the post-shock density given this Mach 15 stream coming in. And you end up with the same magic number just because of the increase by the Mach number square of the density. You're already there, ready for feedback-free starburst. If you have a disk, you can do another estimate, assuming that the collapse factor has to do with the spin parameter. So the number density goes like lambda to the -3, and again you get something quite similar in the same ballpark. And finally, if you just take the mass observed and divide by a size observed, you also get, for this fiducial numbers, 0.3 kpc, which is what we seem to be observing. And the halo mass I was talking about fiducially, again, a number in the same ballpark. Everything points to the density that we want for FFB. Okay, so that's natural. I mean, we didn't have to look for observations. We should have predicted this from very simple theory. This is the density as a function of redshift, and these are the two cases of a shock and of a disk. They're pretty similar. And again, you see that at redshift 10, we are in the ballpark of the feedback and the cooling densities that we derive for feedback-free starburst. So the universe must be doing it around redshift 10. Just to show you where this happens, in the shell case, it's the Jeans mass. So you expect a globular cluster mass scale to fragment and give you this feedback-free starburst. If it's a rotating disk with some angular momentum, you get these clumps, and you can compute, again, clump mass of a couple of 10 to the 6 solar mass, quite similar. Similar clump mass and a similar generation period of 10 to the 9 solar masses. So we can compute what the shell size is. Let me just finish with observational predictions and a summary. So we predict high efficiency in halos just below 10 to the 11 solar mass and above. We predict stellar masses of 10 to 10 solar masses and star formation rate of several tens of solar mass per year. At lower redshift and lower masses, we expect this not to work. Feedback is not going to be quiet for lower masses. You have to be both massive and high redshift. This is the magic stellar density we expect in compact sub-kiloparsec galaxies. A metallicity that is just moderately below unity is good enough. We predict little gas, little dust attenuation. Top-heavy stellar mass function may be there, but it's not crucial for getting this. It's a real efficiency of star formation. You have bursts in generations. You expect cold streams, little hot halo, little outflows. It may be different configurations. I don't know. I just want to show, I'm not going to show the results, but I'm going to repeat my conclusions. We are talking about the phenomena of feedback-free starbursts with high efficiency when the number density is high enough, this magic number density. Then the free fall time is shorter than the delay time in the feedback. If the metallicity is pretty low, the cooling time is shorter than free fall time, and you are shielded if you are above 10 to the 4 solar masses. This is valid at redshift 10, around redshift 10, maybe 8 and above, in massive enough halos because of the post-shock density or because of the clump density in the tumor unstable disks in about 10 generations of starbursts. There's efficient cold inflow streams through the halo, and I just went through a list of observables that can confirm this very simple scenario. So let me just finish with 2 ideas to think about, maybe the crowd here. One of them, people who care about what happens to this galaxy. Remember, we start with a galaxy that consists of 10,000 globular cluster-like systems. Okay, what will happen to it as it evolves forward? Is it related to globular clusters we see today? These galaxies are going to end up today as BCGs in clusters, very big ones. And what's relevant for us, maybe in this workshop, is how is the cosmic web going to be different at redshift 10 and change or help the same picture? For example, in the sense of what is the angular momentum of the incoming streams at these very high sigma peaks at this time? And let me end with this question. People tell me that if you have a globular cluster made of O and B stars, very young stars, it's an ideal place for generating big seed black holes. Because unlike today's globular clusters, these huge stars are going to merge and are going to be disrupted, and build a nice seed. And when you have 10,000 of them in a galaxy, they're going to merge, the clusters are going to merge, the black holes are going to merge. It may be a very nice way to get massive black holes already starting at redshift 10. And let me stop here, thank you.
Thank you, Avishai. Any questions?
Nice talk, Avishai. I have a question about the density. You have this 3,000 per cubic centimeters of special density. And what spatial scale you're talking about having that density on, in the sense that, you know, where we have a lot of detail, say, about nearby analogs of these high redshift galaxies, the group mean square density on scales of hundreds of parsecs might only be 100 per cubic centimeter, but on scales of parsecs, where the star-forming clouds are, they could be several thousand. So,
in today's universe, this is the density within globular clusters. Okay? At that redshift, as I showed you, the whole galaxy will have a scale close to this. And once you make clumps in it, maybe clumps in a rotating disk or clumps in those shells, a factor of a few higher, you're easily going to surpass this threshold and get the feedback-free thing. But in the local universe, that's globular clusters.
So you're suggesting densities this high filling the galaxy. This is you would measure a density this high on scales of
at
half a kiloparsec.
This is over the whole galaxy.
Okay.
The whole galaxy is going to be made of these globular clusters. Okay, that's the prediction here. At redshift 0, it's only in a very few islands like globular clusters. So the key is, the simple idea is that you're talking about a universe that's much denser and a little bit lower metallicity. And that's good enough for everything I just told you.
Hi, Avishai. Very nice talk. So if you look at the GMC simulations, the thing is that usually, you know, if you have the local clumps inside the GMC, you start to form some stars, and that's going to impact your nearby star formation histories. So the question is, how can you hold up those gas with a 3,000 atom-positive
I missed your last sentence. What is the question?
Yeah, it's a question. I'm asking, how those, galaxies with 3,000 atom-positive do not form any stars, before this giant star formation events. Okay, so we have to explain first of all why the galaxies do not have any feedback that can impact the star formation histories, right?
Well, I'm not sure I understand your question, but
he's saying, if I can recast, he's saying, how does these galaxies that are so dense in the first place, how do they hold off star formation in the first place? Why don't they start, making galaxies?
Okay, so you need all these conditions to be fulfilled. You need the cooling time to become lower. You have to build up this density. If you don't build up this density, it's not going to work. So you need to wait for some accretion to happen. You need enough mass to make sure that you can fragment the Jeans unstable cloud. So this takes some time for the accretion to come in. So it's the usual story. You form the halo, accretion comes in through streams. Once you accumulate enough mass, you start building it. And it can start quite early. The whole process doesn't take 1 million years. The whole process takes 100 million years, okay? It takes whatever it takes because gas come in. But it's in each generation going to be leading to feedback-free starbursts of 1 million years. That's the trick. Now, you ask about simulations. That's our next plan, to try to simulate this in many different ways. Both, is it really true that you can have an FFB in a cloud under these conditions with these densities and so on? Is it going to be shielded properly the way we estimate? Everything we did so far is just analytic. Then one wants to do cosmological simulations with the proper subgrid physics that allows all these processes. Most simulations that we have today play different tricks about feedback that may prevent this. So we have to be very careful selecting the subgrid ways to do the feedback properly to allow this to happen. And then you want to know what happened to this huge collection of globular clusters as you move on to lower redshifts. Are they going to be totally disrupted? Are they going to form these huge black holes? lot of work here to do.
Okay, can the next speaker set up, and we can take one more quick question?
I think chemical evolution for feedback-free Starburst galaxies is very effective than the normal galaxies. Could you comment on the high speed of chemical evolution can reconcile with your idea?
Sorry, on the high speed of what?
Chemical evolution.
Did you hear the question?
Yeah,
Chemical evolution. You mean after this? Well, I guess the metallicity will go up and up and up as you build in. The galaxy will continue to evolve in the usual way. After this period, you will have the usual way of more gas coming in, more stars forming, feedback effective, and so on. So this slowly will become normal galaxies, except that they have these excessive early globular clusters in them.
yeah. So I guess what he was asking is, once you have the first generation, you produce all these metals, how does this not pollute the second generation or third generation of these globular clusters and kill this low metallicity condition that you need to form the next generation?
Yeah,
Right.
I don't know.
It's a tough question.
To be studied.
To be determined. All right, let's thank Avishai again.